You make mistakes, which all of us do, but the courage of correction is the only integrity which you need to do. So, I have done a lot to make you confident in one go. Take your time out and listen to this video carefully. And by the end of this video, you will be a super achiever. And without further delay, let's get started with today's topic, that is on integration using residues. So, here the integral is of the type integral minus infinity to plus infinity e power I mx f of x into dx. Now, in this video, I am going to evaluate integral minus infinity to plus infinity cos x by a square plus x square into dx, where a is a positive term, using residue theorem. So, this is the closed contour. So, I'll explain you in detail. So, consider the integral. So, this is in terms of x, and I have transformed this in terms of z. So, here it is cos x and here it is cos z by a square plus z square into dz, where a is a positive value. And see here. Here is the C. C is nothing but the closed contour consisting of a semicircle CR of radius R and the bounding diameter minus R and R. So here C is a closed contour. See, it is a closed contour of a semicircle, half circle CR. So this is CR of radius R and center 0 and the bounding diameter minus R and plus R. Now the C, integral C f of z dz is split into two integrals. So one is from minus R to plus R. So in this direction, line integral minus R to plus R f of x dx, as this is the real axis, plus CR. So CR is nothing but the semicircle f of z into dz. As you know that e power I theta is nothing but cos theta plus I sin theta. So here e power I z can be written as cos z plus I sin z. So this is the question. So in this question, as we have cos z, so I am supposed to write this as the real part of e power I z. The real part of e power I z, in place of cos z I am writing the real part of e power I z by a square plus z square into dz. Now our f of z is transformed as f of z is equal to e power iz by a square plus z square. Now we have to use residue theorem. So in order to find the residue theorem, first of all we have to find the poles. So for finding the poles, as usual, we have to equate the denominator to 0. So this is a square plus z square is equal to 0. So z square is equal to, this is minus a square, z is equal to root over, this is minus a square, and z is equal to plus or minus ai. So z is equal to plus ai and this is minus ai are two simple poles. So these are the two simple poles. Now what we have to do? So we have to check whether these poles are within or on or outside the given contour. And the contour is like this. So this is the contour. So this is minus r and this is plus r, and this is a real axis and this is y-axis, this is 0, and this is a semicircle with radius r and center 0. So this is a CR, that is mod z is equal to r, and see, it is easily identified as, so plus ai will be here and minus ai will be outside the given contour. As usual, that is plus ai is within the contour and this is outside the contour. So this is the closed contour in which ai lies inside the contour. So within this contour we have to find the residue. So how to find the residue for the interior pole? The pole is within this one. So for finding the residue of f of z at point z is equal to z naught, as it is a simple pole, the formula is also so simple. Limit z tends to z naught, this is z minus z naught into f of z. Clear? And now see, what is our z naught? Z naught value is nothing but limit z tends to ai. This is z minus ai into f of z. So what is our f of z here? F of z is nothing but e power iz by, this is z square plus a square. So after substituting f of z value, so this is the residue value of f of z at the interior pole ai. And see, this can be cancelled as limit z tends to ai, this is z minus ai into e power iz by. So this can be written as z plus ai into, this is z minus ai. Now I can easily cancel these two and substitute in place of z as ai. So this is ai and this is again ai plus ai. So this will be I square value is very clear as minus 1. So here I square minus 1, this will be minus a by 2ai. So this is nothing but the residue of f of z. For the interior pole, z is equal to ai. So for the interior pole, z is equal to ai. So this is our residue value. So after finding the residue value, so we have to apply the residue theorem. So this is our residue value. The residue of f of z for the interior pole z is equal to ai is nothing but e power minus ai by 2ai. Now I am going to apply the residue theorem. So the residue theorem statement states that after applying in the residue theorem, the theorem states that integral c f of z dz is nothing but this is 2 pi I into this is sum of the residues at interior poles. At interior poles, therefore integral c, this is f of z dz is nothing but this is 2 pi I into e power minus a by this is 2ai. Now I can cancel this 2i and this will be integral c f of z dz value is equal to this is pi by a into e power minus a. So what is our integral c? So integral c is nothing but the closed contour. So as usual, this is the closed contour from minus r to plus r. This is 0, this is x-axis and this is y-axis. And this is a semicircle with center 0. That is cr is equal to mod z is equal to r. So here is the direction from minus r to plus r and through this semicircle. So here the bounding line here is from, this is from minus r to plus r. This is f of x into dx plus minus r to plus r, and through this cr semicircle, that is f of z into dz value, this is pi by a times of e power minus a. So this is equation number 1. Now we have to evaluate these two integrals and we have to add up so that we'll be getting the final answer. So here this is integral minus r to plus r. What is f of x? F of x is e power ix. See here, this is e power ix by a square plus x square into dx plus integral cr. This is f of z dz is equal to this is pi by a into e power minus a. So here, as r tends to infinity, as we tend r to infinity, so what happens here? So this will be integral minus infinity to plus infinity e power minus x by this is a square plus x square dx plus integral cr. This is f of z dz value will be this is pi by a times of e power minus a. So as r tends to infinity, let me give you clarity for this. So integral cr f of z dz. So f of z is nothing but e power iz by a square plus z square dz. So here is a small substitution. We have to keep z is equal to r into e power I theta. If I take modulus, so here mod value, that is cos theta plus I sin theta. This will be root over cos square plus I sin theta. Mod z is equal to r. So as there is dz here, we have to make a derivative. Again the same substitution, z is equal to r into e power I theta. Dz value is equal to r into, for e power I theta, this is e power I theta, again I into d theta. If I take modulus, so e power I theta value is clearly as this one 1, and for I can be written as 0 plus I into 1. This is root over 0 square plus 1 square, which is equal to 1. These two are 1. What remains? R into d theta remains. So in this integral, so in place of z, if I put r, so in place of z, if I put r, in place of dz, if I keep r into d theta, and see here, so this is less than or equal to r in by r square minus a square. If I take r common in the numerator and this one r square in the denominator, if you cancel, r remains in the denominator. So if I put r is equal to infinity, so 1 by infinity value, this value is 0, as this value is 0. So now I am substituting this value as 0. So I have given you a clarity there, and there is no need to write straight away. You can write like this, and see here, e power ix can be split into, so this is minus infinity to plus infinity, this is cos x plus I sin x by this is a square plus x square into dx plus 0 is equal to this is pi a by e power minus a. So if you split this as the real part and the imaginary part, so this is the real part and I times of this is the imaginary part, that is a sin x dx by this is a square plus x square. So this real part is pi by a e power minus a plus I times of 0. Now equating the real parts, so these two are the real parts. So equating the real parts on both sides, equating the real parts on both sides. So we'll be getting, see, integral minus infinity to plus infinity, that is cos x dx by, this is a square plus x square value is pi by a times of e power minus a. So this is what it is asked in the question to show that, see, integral minus infinity to plus infinity cos x dx by a square plus x square using this theorem. So back to the beginning, see here, this is the integral. So this is the contour, and see here, so we have two parts here, and e power iz can be written as the real part of cos z. In place of cos z I have written the real part of e power iz. So here is our f of z. So f of z value is this one. So for finding the poles we have to equate the denominator to 0. So these are the two poles, and after that ai is within the closed contour and minus ai is outside the contour. So for the interior pole I have calculated the residue value, and this is the residue value, and after finding the residue value I have applied in the Green's theorem. So Green's theorem is 2 pi I times of the sum of the residues, and this is the final answer. And see, this c is split into two integral levels. The first one is minus r to plus r, and this is around the semicircle, and after that one I have given you a clarity why this one is 0. As r tends to 0, this one is 0, and this is ix can be written as e power ix can be written as cos x plus I sin x, and this is the real part and this is the imaginary part. After equating the both the real parts, we got the final answer as pi by a e power minus a. This is how we have to solve, and I hope that you will take some of what I have told today. And thank you so much for listening. And if you really like this video, please practice, go through this video for one more time. If you don't understand, please pass it on to your friends, siblings, and the person you like the most. And thank you so much for staying.